Good.
All right.
Oh, yeah.
How's it going, everybody? I appreciate you coming here, particularly considering tomorrow is July 4th and we are all off as soon as this is over. So I'm going to roll through this, pun intended, as quickly as possible. My name's Andrew Estes. My thesis was Poisson analysis of Formula One pit stops. Basically, I was trying to predict when a pit stop would occur during a Formula One race. The first thing we need to understand is different types of data. Ours with the Poisson distribution, the probability that an event may occur or does not occur. In our situation, does a pit stop occur or does not occur? The other distributions here don't really matter, but this is for your education. To keep it simple, a Poisson distribution has to deal with count data. Here's an example of height based upon gender. As you can see, there's roughly 120,000 women who are roughly 160 centimeters. All right, so we all have statistical expertise. You're welcome, and you guys can give me tips on the way out. Now we need to start talking about F1, also known as Formula One. Formula One cars are the fastest growing racing cars in the world. In 2020, a driver averaged 164 miles per hour through a lap. In 2005, a driver hit 232 miles per hour. But this isn't a drag race. There are lots of curves and turns that need to happen. In fact, when they brake, they go up to about 6 G-forces when they brake from the 200 down to 60 miles an hour. Put that in perspective, the Apollo 16, that was the last mission that put men on the moon, they re-entered the Earth's atmosphere at 7 G-forces. So these drivers are right on par with those astronauts re-entering Earth's orbit. The picture you can see here is the starting grid. There's 20 cars here. There's 2 drivers per team, so there's 10 teams. And they're all fighting for places. The higher you place in the race, the more points you get. That goes, pretty obvious. And then the 2 drivers for your team increases your team's overall points. And what you'll see here, if you want to look at McLaren, like Lando Norris is in the orange, he is the 7th best driver, but McLaren itself is the 5th best team. And that's because those 2 drivers under him actually surpass Lando Norris's driving points and his teammates' driving points. There are over 20 races per season, and they cover 5 of the 6 hospitable continents. Here's the picture of where all the races have taken place in F1. Within each country, there are multiple tracks used. So you can see United States is the 4th most visited country, but also the highest variety of tracks within the country. And then you got some like Morocco, who's only been visited once, so therefore it only has 1 different racetrack. Here's the breakdown for the years that we're covering. We had 5 years, and we had 27 countries with a total of 103 races. And there's a variety of the races per year, and there's a variety of which countries are visited every year. For example, Australia was not visited at all in 2020, and Italy was visited 3 times. 2020 was the year of COVID, so COVID regulations had a lot to deal with the frequency of visits during that span. And if you look at the subtotal, you can see there's a good variety of frequency for each country. With each country comes different climates. And as you can see here, we got a good range of temperature. If you look at the track temperature, it's about 100 degrees difference between the lowest temperature and the highest temperature on the track. That plays a role with tire life. As you can imagine, 150 degree weather is not great on tires. The humidity range is also pretty impressive, as 95% of the range has been covered. And something for us statistical people to look at is the air pressure. Looking at the standard deviation of 49 and the average of 986, the lowest of 779 is way outside the norm. That's about 5 standard deviations outside what we would expect, which is just absolutely crazy, I think. With the different climates, with the different countries, there's also different layouts of the courses. So here we've got 2 races in 2018, one in France and one in China. It's pretty obvious just from first glance that the 2018 Chinese course is a lot more curvy than the 2018 French course. You can actually see that when it comes to their gear speed. So these colors correspond to the gear the driver is in when they go through the lap. And this is the fastest lap. So the fastest lap, the fastest driver, these were the gears that driver was in. So eighth gear is obviously the highest gear, the fastest you're going. They only hit eighth gear once in China, and they hit eighth gear 3 times in France. Similarly, in China, they went all the way down to second gear once, and they didn't even hit second gear at all in France. So we've got a lot of variety when it comes to the layouts of the tracks and how that kind of plays a role. Another crazy track difference is there are street tracks and there are race tracks. So this is Las Vegas. I don't know if you recognize it. It's okay if you want to plead the fifth. They're having a race here in November, and this is where it's going to be. It's going to cover this entire span. So it's going to be right on the strip. Yeah, that's right. It's crazy. You'll see something pretty crazy when we get to Monaco. But as you can imagine, these street tracks is what they're called, and they have a lot more variety and provide a lot more issues than a dedicated racetrack does, because you're dealing with regular pavement and regular roads, and you have to create this course out of something, and you have to block off all this traffic. So there's a lot that goes into these street tracks. Here's Monaco. It's insane. You go off the road here, you're going to run into this apartment complex, and these people might fall down. And not only that, but I mean, look at the curve is just so tight. I should have used artificial intelligence to actually determine the angle, but there's an incredibly tight curve, and the elevation change is pretty sweeping. You can see the Rolex sign in the background, how big that is, and it's still not all the way at the top of the track compared to the bottom of the hill. Now we can compare that to Austin. This is a dedicated racetrack. It's fairly flat, it's not as tight, and there's not nearly as many dangers, but the roads are typically a little bit better than what you see with on the street. All right, now that we're done talking about tracks, my analysis was done on pit stops. And what you'll see here on the left-hand side is the pit lane, and there's actually a car coming out of it. And that is also where the start and finish line is. It looks kind of clean, but it's really not. Here's another view of the pit stop lane. You can see that this red car is trying to exit at the same time as this blue car is. And the orange team also has a car in there as well. With all of those 3 cars there, there's still all these people on the side waiting for their car to come in, or they're just getting done with their car and they're trying to clean them out. There are 20 people on a pit stop crew, and these are their various rules. There's roughly 3 to 4 people per tire, and then you got people who jack up the tire. I'll let you take a look and look at the various rules or various roles they have. All right, here's a picture in real life with real bodies and not just a graphic. It's super tight, and you got to keep in mind that you have these cars that are coming in and rolling up right on the side of you. So if you take a step or two out into the pit lane, you're going to get run over. They don't have horns. All right, now we're going to take a quick look at a pit stop. And circle here. Make this full screen.
Slideshow. Click on the thing on the side to see it to move it. It's jiggling at you. That guy.
Okay. So 2.1 seconds was the time. Now, to put that in perspective, if the entire population of Kirksville got their tires changed in the same day, it would take less than 10 hours. I would take that. Right now, it takes me about 4 hours to get my tires changed. All right. Now, here's a snapshot that I took 1 second apart, actually a little bit less than a second apart. Other than the weird angle, did you guys see any differences? Yeah, did you say the red? Yeah, the red stripe and the white stripe on the tire are different, and that signifies that a different tire has been used. In fact, there's 6 different types of hard or dry compound tires used, ranging from like very soft to very hard. There's also intermediate tires and wet tires, and you have to use 2 different compounds per race, at least 2 different compounds. So you can't use, C3 and C3 if you're making a 1 pit stop race. You have to use C3 and C4, for example. And this plays a role because different tires have different degradations on how quickly they fall apart, basically. The people who make the decision to come into a pit stop and what tires to use are called race strategists or chief engineers. There are these people you see here. They have a lot of information coming on the road. They have roughly over 150 sensors on the car, measuring everything that you can imagine and more. Over 3 terabytes of data are generated. And they got to keep in mind the positioning and what's going on with other drivers, as well as weather, because that plays a role. The other thing they have to consider are flags, which are a huge difference. There's 10 different types of flags. A yellow flag is the one we're most common with. It's a caution flag or a warning flag, and basically forces all the drivers to slow down by 40%. The reason that's important and it affects pit stops is if everyone's driving 40% slower, they're driving less than 80 kilometers an hour, then the time you spend in the pit stop is not going to be as impacted as if they were driving 160 kilometers an hour. I mean, basic math. If they're going around the track slower, then when you're not in the track and not racing, the time loss is less affected. In fact, it's about 4 seconds less of an impact. And when you're talking about things measured in milliseconds, that's a huge difference. All right, I've got one other question. We're going to go back to Austin because it's just south of us, a couple of hours. Does anybody have any idea where this racetrack starts and stops? Keep in mind, lower gears probably have something to do with it.
Looks like maybe on that U on the top.
Are you talking about right here?
A little bit to the right there.
Right here?
Right there, yeah.
Okay.
The upside down U, I should have said.
Yeah, upside down U. I see it.
Yeah.
Yeah. You are close. I can see why you would think that because that is the slowest typically. But the other thing to consider is pit stop lanes also come in where the tracks stop and start. So having a pit stop lane in this closed turn section wouldn't really be feasible. Anybody else want to wager a guess? I mean, it's very hard. I had to look it up.
On the orange straightaway? Along the top?
No, that would be my guess.
Yeah.
The actual one is over here in this corner. It starts here. That way the people can make their pit stop. And what they'll do is they'll just kind of follow this curve into here like that. And that gives them enough space to make those changes and everything else. I also inadvertently told you where the race was headed by going like this. It heads from this corner down to this corner. All right. Any questions for me on the basics of Formula One racing? All right, seeing none. Let's get into data. Let's get into the data now. All right. First step, after you decide what project you're working on or what you're told you're going to work on, if you're in the corporate world, is getting the data. This was all done via Python. There is no other way to access it unless you want to build your own API and try to gather the data yourself. Here's a snapshot of the 500 plus data frames that I had to create or gather. What you'll see here is if you look at the Abu Dhabi race 19 laps, third down, and then look at the one at the very bottom, that the rows and the column sizes are that the row sizes are different. And that's something that's pretty common throughout. Each race and each year has a different number of observations. And this is what the last data frame had. 27 columns is basically covered timing data. So what the driver did, when the lap was started, how fast it took, things along those lines, who the driver was. And then we had the results data, which is a very simple 16 columns by 20 rows. The 20 rows are for all 20 drivers and tells you what place they finished. So first place, second place, you can judge that by the number of points that they received. We combined those two data frames into one by driver, grid position, position, and points. This helped tell us what position they ended up in by getting the points. And the grid position was their starting position, and then driver was how we merged them together. A data frame we would have liked to consider, but wasn't really worth it, was the race control messages. These came from the director of the race, the person who's kind of in charge of everything. And what they do is they call the flags. So you'll see 4 down, there was a yellow flag issued in track sector 2. But they can also call flags directly to specific drivers. And that is kind of important because it tells drivers if they need to slow down or if they actually have to come in because their car's too damaged to stay out as is. And you can see that for the blue flag at the very bottom on observation 10 that Pierre Gasly had a blue flag and he was forced to come in there. The second data frame we didn't consider, and really would have loved to include this as the weather data frame. We kind of went over this in the introduction. Weather is just so important to how the cars handle and how the tires survive. And it plays such an impactful role. However, if you notice, the time for this data is done on the minute, every minute, and there wasn't a way to combine that into our existing data frames. So we did lose a lot, I think, of predictive power by not being able to include this observations. I couldn't think of a way to do it. It's just an unfortunate loss. What you'll see here are just some snapshots of the data. A lot of my thesis is done on data transformations, wrangling, and cleaning. Had over 2,400 lines of Pythonic code to get all of these data frames merged and cleaned up and prepped together. I had to add names to the data frames. I had to add years to them. I had to merge them all together so we would actually know on an annual basis as well as the 5-year basis what we were looking at, rather than just looking at each race individually. I also had to throw it into a CSV file as well for our analysis, and we'll get to that in a little bit. But once the data was wrangled, we created our R-Shiny visualization to help look at what we had. This first one's nice and pretty, and it's the prettiest graph you have. I apologize in advance that nothing else is as pretty as this. So enjoy it for all its glory. This is looking at the lap number or how frequently a team came in for a pit stop. Color-coded by team, and we also did the same thing for drivers. And it's for a specific race over a period of time. The issue with this data is not all of these teams were active for all of the years studied. For example, like Toro Rosso and Saubauer, apologies for their pronunciations, they don't race anymore. They haven't raced since at least 2020. So their number of pit stops for this specific race is obviously going to be less than Red Bull, who's raced every single time that this course has been available. We had the same issue with drivers as well. So what we then looked at was the tire life when pit stops were made. As I've kind of made clear, tire life is very important when it comes to pit stops, because you can't drive on unsafe tires. You're just going to lose a lot of time, and also it's very dangerous for the driver and everyone else. It follows a pretty, I'd say, fairly normal distribution. It is right skewed to an extent, but there is a clear curve, bell curve, I'd say, with the height of around 20 laps. And 20 laps makes sense when you think that most races are around 50 laps long, 50 to 60 laps. So that lets them race around half the course before they come in for a pit stop. We then looked at the lap number when the pit stop was made, and that was severely right skewed, with the highest being 77. The reason for this is simply due to the course layouts themselves. Let me get the numbers themselves here. The lap number 77 relates to Monaco, which we showed earlier. It's in that small country right on the coast, on the street. So they have very limited space of which they can operate their F1 course. So they actually have 78 laps in Monaco, and they cover 161 miles. On the flip side, you have Belgium, which has 44 laps and 191 miles. So 30 more miles and 34 less laps for Belgium. And the reason that you can see like these small outliers towards the end is because drivers want to get what's called the fastest lap. If you get the fastest lap of the race, you get an extra point towards your standings. This actually happened yesterday in the Austria race, where the driver pitted on lap 70 to get the fastest lap, and the course ended on lap 71. So you can see those things, but typically there's a uniformish distribution between lap 20 and lap 40. The high frequency you see in the first 5 laps relates to weather and accidents. In Japan, there was like a massive rainfall. It was kind of monsoon-like. And so everyone was on wet tires to begin the race, and then they had to switch their tires to something else because the rain just disappeared around lap 3. So all 20 drivers came in at lap 4 to get different tires that were better suited to the field. And likewise, as you can imagine, if there's a big accident, everyone has to come in, then there's a massive pit stop change there as well. And there's a lot more accidents and flags at the start of the race than at the end, because everything's still getting sorted out and everyone's still fighting more towards the beginning than towards the end. All right. So now that we got some visualization done, we did some basic analysis. We're dealing with Poisson, so we did a mean variance analysis. We looked at Saudi Arabia by itself, and then we looked at all courses. Saudi Arabia, you can see the variance was about 3 times as high as the mean, and the variance for all courses over all the years was about 10 times higher than the mean. That's obviously over dispersed data and isn't what we would like to see, but it's what we got, and so that's what we worked with. We created a data frame for pit stops to help us look at that. And what you can see here is just the breakdown of the frequency of the pit stops and what lap number those pit stops were taken at. It's kind of interesting to see, for example, this on index 13, the very first row, someone took a pit stop at lap 24 and then did not take another one. And then at lap 18, someone took a pit stop at lap 24 and then took one another 4 laps later. The reason for this could be any multitude of reasons. It could be car troubles, it could be an accident, it could be strategy decisions. But it is kind of nice to see where these frequencies come in. And you'll notice most of these pit stops come in at around lap 20, except for this weirdo who did it at lap 5 and did not do it again. With that data, we then actually looked at it and graphically visualized it. We looked at actual number of pit stops and the normalized number. About 80% of all pit stops, the frequency of pit stops were either 1 or 2 per race. To get a pit stop with to get a race with more than 2 pit stops was more rare. It took about 20% of the time. And that's what this data shows. I have no idea why people took 7 pit stops. There's zero reason for that. They just had to have car issues, and that's just what you do to finish the race. All right, now that we've done kind of the basic analysis and the basic visualization, it was time to start our Poisson analysis and get a little bit more statistical. So we ran the Poisson analysis. We tried doing it via the scikit package in Python, but it didn't work out. And then I found another Poisson regression model in the stats model package, and that worked fine. And that's what you'll see here. Pretty much every single variable we have is significant, which is also not what I would like to see. I would like to see some variance and help telling me what's going on. And since the data was over dispersed, we're not really sure regular Poisson was the way to go. So we moved on to consoles Poisson, which is better for over dispersed data. It's called GP1, I believe. And that worked for the most part, but we had several variables come out with errors, log likelihood errors, and there might have been a rank deficiency error as well for one of them. But we were able at least to get a little bit of results here. The third one we tried was fam-loss Poisson. And I brought up this tire life picture again, because the way fam-loss Poisson is described, it has to deal with a skew distribution that kind of turns more normal as the location parameter gets more vibrant or more significant. And I think that fits this distribution here pretty well, pretty accurately. Unfortunately, when we tried fam-loss Poisson, every single variable had an error. So we got 0 results, but that's okay. So we were like, all right, over dispersed data, negative binomial. That's our one. So we got negative binomial. There's two models, negative binomial 1, negative binomial 2. There's probably more than that, but I found this book on negative binomial regression by Joseph Hilby, who's like a member of the Royal Statistical Society. So I assume he knows what he's talking about. So I kind of followed what he was doing, and he said use NB2 when you're dealing with over dispersed data. And one of the things he gave us was this ability to calculate the alpha value, or the estimator for over dispersion. And so this was the picture in his book. And I found a kind of a step-by-step breakdown of how to actually calculate this alpha value. And we can go here. So the alpha value we got was a negative, and alpha is, yeah, exactly. Alpha should be between 0 and 1. And so I was like, this is fine. This is exactly what I'm expecting. I'm expecting failures on Poisson, consoles Poisson, fam-loss Poisson, negative binomial, just everything's fine. It's all on fire, but whatever. I got some coffee. So what I did next is not proper statistics, but I did want to show some data science-y stuff. So I took the absolute value of that negative alpha value and then continued analyzing it as if it was accurate. I just wanted to show that, hey, we can actually look at predicted versus actual values with negative binomial, assuming our data and everything else was good. And as you see, I mean, it worked out pretty well. I took the t-test and it was statistically significant. It's just not valid because we had that negative alpha value. So negative binomial failed. Our next step was random forest. We did a random forest for just the Saudi Arabia race, and it actually had an 80% accuracy rate. And I was like, oh, that's awesome. I got something that's working. Let's go. And we got the importance variables here, and then I applied it to the full course load, and the accuracy was 42.6%, which is not awesome, not close to 80, and it's not better than 50-50. So random forest got thrown away too. So I went to the the gorilla throwing paint at the canvas method. and we went to quasi-Poisson and a bunch of other methods just trying to make it work. There is no quasi-Poisson package in Python. So I had to, but there is an R. And so what I tried to do was backdoor the R script into Python. I found a way to get all of that working, and it would change the Python data basically into the R data frame. And it would let you call R script within the Python IDE that I was working. And it worked out. I was able to change it into our data frame, and then I was like, oh, let's call it GLM, because that's what you use in R. And it said GLM not found. Like, oh, well, that's not working out. And I need GLM for everything that I'm going to do. So I just went back to the CSV file. I wrote it back to CSV, and then I accessed it via RStudio. Then I had to re-clean everything. I had to codify all the string variables as factors and do all that other kind of basic cleaning that was lost in that push to CSV. Ran regular Poisson because why not? Got it like a 22,000 AIC. Then I ran quasi-Poisson and did not get anything. It was a non-applicable result. And then what did I run next? Then I ran negative binomial. And that also had a 22,000 AIC. So the negative binomial and the regular Poisson were essentially the same effect in R, and quasi-Poisson didn't work at all. When I was doing this research, I found in one of the CRAN documents these other packages, FlexMix, G, generalized estimating equations, and then the nonlinear mixed effects models. And none of those worked for various reasons. There was either errors or NMLE required Gaussian distribution, which we didn't have. So I couldn't really work further with that. So my next step then was Senior Bayes. These are the steps I followed. I don't have any pretty graphs like I wish I did, but basically what I did was I simulated the normal model. I did these checks that you see here. And I just got a bunch of errors, a lot of convergence errors. I upped the chains, I upped the iterations, and none of it worked out. But conceptually, I had an idea of what we would have done. You know, we would have done like an MC trace to do the comparison of the simulated data to real data. We could check the histograms to make sure everything rolls out that way. And we could have done some confidence intervals as well. But I couldn't do any of that because I didn't have anything besides errors. All right, questions?
Okay. Okay, question.
Let's back it up a little bit. What is your why? Is it number of pit stops that you're stopping, or what?
There's no lap number.
That number.
We were trying to predict when the pit stop would happen.
After how many?
Yeah.
When did it happen? It's not necessarily bottom zero.
Yeah, because I did look at a zero model matrix or zip and hurdle. Yeah, zero and slated. Yeah, so I looked at zip, but we didn't have that. We didn't have any zeros.
Everybody stops somewhere.
Stopping time is.
Yeah.
One of your histogram has a little bit of zeros, couple zeros, one left. Right, that one, but it's not.
It's not zero.
Yeah, it's not. Yeah, because so I'm just gonna stand in front of you. So the issue, if we try to go anywhere above like here, not every race has those laps. You know, Belgium only goes to lap 44, and then there's no one's ever going to take the lap on lap number 1 because you just can't physically do that. Take a pit stop on lap 1.
Right, because when you finish the lap, it's 2. Right?
Yeah.
So I'm just thinking, you know, when you are trying zero inflated Poisson or zero inflated negative binomial, that typically works real good when you have a whole bunch of zeros and then.
Yeah. Yeah, I brought that up to Dr. Bergosco, and she's like, yeah, we don't have any zeros.
In time, be of different nature. Okay. So. Is it? I guess, is it more important to count how many times they stop, or is that important to predict when they stop?
So the goal is to predict when they stop. Because this was done with the idea that we can do some sort of strategy. Like, oh, we'll predict driver A is going to stop at lap 20. So we'll change our strategy to stop at lap 23 or whatnot. And so that it was more from a strategic analysis viewpoint that we were addressing this question.
For your question, when they stop was it?
Right, and I think if you were gonna start over, like, by the time I thought of this, I was totally not gonna have him. But I think you'd actually like normalize it by how long each race is or how many miles each lap. Like you would do it by how many
Yeah.
miles when the.
Yeah,
pit stop.
I didn't think about it till you asked the question
Right.
about that.
No,
I was like, oh, you can't do it. Yeah, I was like, you can't
Right,
analyze.
I thought of it like 3 weeks ago and I was
Oh.
like, I'm not even gonna bring it up. So, but I think if you did something like that, because that idea that the tracks are so different, that would help you control for that. But even the idea that some of the tracks are super boring, that they have almost no elevation change and way fewer turns than that Monaco. I mean, that Monaco one's famous for how ridiculous it is that you're basically driving off a cliff and doing a hairpin turn at the same time. But that idea, and so I think, like I said, now that we've done it, I think I know how I would approach it. That if the next person comes along and wants to do it, I think you would say, we're going to use bootstrap techniques. We're not going to do any of these kind of models. And we're going to do some, and even, I don't know which kind of normalization you would do. Would you do it by like percent through the race? Or
I
miles
would
in
say
the race?
percent through the
Because
race.
the races are mostly all the same overall length, right? They're 310 kilometer or whatever. There's some, it's a pretty tight overall length of the race. But anyway, I think if we were starting over, we would do a totally different project that would maybe get a result. But like I said, that wasn't until we did the project. I don't think you would have known how to do the project. And maybe just, you know, Americans shouldn't look at F1 racing because we're dumb and bad. F1 racing. But
Yeah,
go ahead.
like, sort of my thoughts were on similar thing, but like looking at your random forest and whenever you stuck with Saudi Arabia, you got good results. Everything. Is it just that the tracks are too different?
Yeah.
Like, is it like, do you think that having a model for Formula One, even with normalization, is maybe like,
Too aggressive
or too optimistic?
Yeah.
That like if the tracks are so different, did you do more? Like whenever you saw that the random forest worked really well for Saudi Arabia, did you look at individual tracks other than Saudi Arabia?
Yeah, so that's actually in my paper itself. I do think that a better analysis would be looking at the courses individually, as well as maybe looking at the courses over that period of time. Because we do see, like, you know, in the very first data frame snapshot I showed you, Saudi Arabia had 2 different rows, number of observations of the rows. So even a year-over-year analysis of the same race could lead to significant differences. And that is something to consider. I do think looking at them race by race would be the best way to go. It would just
So
require.
I think your original question, I mean, the idea that you were trying to do predictive strategy. So even if you were to imagine, hey, because they do change the courses every year and they change the city. So if you said,
Monaco's street race.
so Monaco's Monaco's they do every year and it changes a little bit, but it's kind of more standard one. But like Korea had a Formula One race like twice, right? It was. There was a big thing that South Korea hosted an F1 race. But how would you prepare for that as a team? That you've never been on that course. You've never been, and the Las Vegas one, they change, and of course, they totally tear down Las Vegas and rebuild it every 10 years. So
Yeah.
you have to, but that course is, other than I think you go past Caesar's Palace because they do good pictures every year. But other than that, I think it's different. In fact, I think Caesar's Palace
And
sponsors
then the
it.
climate would be the other big consideration, because as I said, in Japan, right, in 2022, you had that massive monsoon. And that's not going to be the case every single race. You're not going to have that massive when they start. In fact, there's a famous picture of a driver driving right by a tractor because they didn't call the red flag. So he was going, 150 miles an hour, and there's a tractor, like a big old tractor right next to him, and he was upset.
Sure. But Las Vegas, you don't need the wet tire, you probably can bring the wet tires to Las Vegas, right?
Yeah,
And so that's the question that other than going, we can't predict anything ever.
I went from knowing nothing at all about Oracle, not really interested.
Exactly. Now I feel like I need a non-stat question. How is the F1 is different from?
NASCAR.
Yes.
Turns, super different,
I'd say turns is the big thing.
How?
because they have a big square.
So it's just course is different?
Yeah, well, so like in NASCAR, it's just an oval, like a donut.
Okay.
And
You
then-
just go circle.
Yeah.
Right.
And the
And
cars
here
are,
you
the cars are more
see-
like cars. Formula One cars are very particular, right? NASCAR cars aren't actually street legal cars, but they look like them.
Yeah, bodies.
Well, you
Just
just-
like a Toyota Camry on steroids.
Were there American NASCAR people actually drive for F1 too? or-
There is an American this year. He's from Florida. His name's Logan Sargent, and he hasn't scored any points this year.
What about American
And the
company?
other way, Danica Patrick started as that, and then she moved as the famous woman driver.
Which car manufacturers participate in Formula One? I know Honda does,
Not anymore.
not anymore.
No, they'll provide like the engine or something like that, but there's different like brand names, like Red Bull is the best like Formula One team out there, and they're not a car manufacturer. They're just they just provide the money.
Right, the engines
front
are all
the money.
Ferrari engines, right?
Right, then who
Yeah.
produces
Powertrain
those
stuff like
cars? Who makes those cars? Racing
Who
cars.
makes them? Yeah, they have an entire team of engineers
Okay,
who.
so it's their own production, they just getting kind of parts from different.
So they'll all share like the same like power drive or powertrain. I'm not a car person.
I think,
so-
yeah, half the cars are the same for everybody. And then you only get to custom, and so like NASCAR is the same way, there's only like 3 cars you can have. And then you can't even do a lot of things to it, but
So what are independent variables that you use?
That's another question.
there's like 100 of them.
Yeah.
19 variables that you list in the table. What are those?
I would have to have that pulled up in front of me too. Because I don't remember off the
No,
top of my
no,
head.
okay, because I can't find exactly in the text what those are, and it's really interesting what you have.
Yeah, all right. So basically we have the driver. We have used the driver as a independent variable. The tire compound as one, the tire life as one. There's a category called fresh tire, which, to back up, prior to the actual race that happens on Sunday, there's 2 practice races and a qualifying race, and occasionally there's also a sprint race. The qualifying race is what gets you your grid position to start with. And you only have those sets of tires to work with. You don't get to use unlimited amounts of tires. And so fresh tire analyzes whether that tire's been used before or not. We use stint as a variable, and stint says basically have they come in for a pit stop yet or not. If they're on their first stint, they have not come on to a pit stop. Once they go through a pit stop, they'll be on their second stint. Team is another variable, just like driver. We use year and race as ones to try and separate them. Because as we've explained, there's a massive difference between the tracks and each year itself. Track status is what we used as well, and that has to do with the flags, if it's a yellow flag or what the issue is there. We did start with the grid position, which is their starting position. The reason we did that is people towards the back of the field will choose a different tire compound to start the race than people at the front. Because people at the front really need to get that fast get off to maintain their position so they don't get thrown in the back, whereas people in the back can just chill with a harder compound, and that hopefully gets them caught up later down the line.
So even that, right? So a soft tire goes faster, but it wears out faster. And a hard tire doesn't go as fast, but it lasts longer. And so that choice, and then there's this whole thing about over the qualifying and the race, they only get so many tires. So if you use too many brake tires during your qualifying, you don't have any left to use during the race of that kind.
So kind of.
Yeah, kind of strategy like that. And that's why I think I think this question is really that I think, and I think even those people, you showed the picture of the people near the beginning, but those people would say, oh, I don't use statistics, it's my field. And then they look at 500 variables, but they can't even explain which variables guide their decision. They are a AI model of themselves. They can't explain their.
So, I'll probably shut up.
Oh, but it's
No,
okay.
I mean,
I'm kind of curious because, you did a lot of different kind of statistical modeling. One of the variable is the driver.
mhm,
Driver means this is whole categorical variable.
Mhm.
It's not numeric variable at all. How did you handle that? Because, if you just run categorical variable, with a whole bunch of other variables, how you're going to interpret that coefficient to have it.
Yeah.
That's just totally different.
Uh,
So, how did you handle it differently, or did you handle it just same as quantity?
well, we just factored them. We made them a factor,
Okay,
so.
okay.
yeah.
Okay, so they just take R or Python take care of it.
Yeah,
Question. Why would hitting on the second to last lap help you get the fastest lap in the race?
because you can then throw on the soft tires, and you also have less amount of fuel, because you have to carry fuel for the whole race. You can't add fuel in.
You're lighter.
And you're losing, so there's
And you're
fewer
losing.
cars.
Well,
But there's fewer cars. The other cars are out of the way.
Well, actually, the guy who did it yesterday was actually winning. He was winning by 23 seconds, and a pit stop took 20 seconds to do. So he's like, I want to pit. And like, all right, come on. And it was risky. It was like, everyone's like, oh. Because if that pit stop took just a little bit longer, he would have lost, 8 points pretty easily.
And you risk 8 points to try to get one.
Mhm. But, it's like killer mentality, I guess.
Right.
Where was the truck?
Right. People online, do you have questions? We're just having a conversation.
Okay.
We're all just learning about Formula One racing, I guess, as part of it.
But my only, it's not even really a question, it's just more about your study was on the characteristics of the cars, and it's a lot of this is over my head, I'm still learning about it, but it'd be interesting to see the characteristics on each, maybe each of the top 10 tracks, and how does that impact the performance? Like, is there a home court advantage, so to speak, for the tracks,
Yeah, no, you're definitely onto something. There are drivers who perform better at specific tracks, for whatever driving reasons they have. Some people do a lot better on streets than the dedicated racetrack. Some people do a lot better at the Canadian racetrack than every other one. It's very, I think, driver dependent, but a lot of the variance that comes to the results has to deal with the car itself. There's been several studies done that show 86% of the results or the variance and standings come from the car construction. Only 14% comes from the driver skill.
Oh, okay, that's interesting. That's a good nugget there. Thank you.
Yep.
Anybody else online? Oh, go ahead.
So there is this self-driving cars. So if it is really, very depending on the driver, do you see the self-driving car have its place to compete in the F1 race, or?
I think it'd be, oh, go ahead. Yeah, you answer. You
Yeah.
don't think.
No, I mean, I've never thought about that. It's out of the box, but I like it. I think it'd be super interesting because the car itself could theoretically read all of this data and understand it better than the humans who are trying to look at everything. So I think there is some validity towards that.
What I learned from 80s TV shows is the computer car
Right.
wins the race all the time.
The DeLorean.
The Knight Rider. But I think, I was gonna say Formula One seems more like, I think NASCAR, that would make a better sense because it is such an oval track that, but like those weird bends, it seems like that would be harder to, and I suppose if they were all self-driving cars, that would be a lot safer.
Yeah,
Nobody would watch.
right.
Yeah.
So what's the? Let's be just.
Good point. I don't know. But, all right, cool. And I think the other thing is that, you're sort of our first master's student who you don't have kind of this ta-da result, and it's, you were sort of, well, but you were sort of gloomy about it before,
No,
and you seem like you're through it, so that's good.
no, not really gloomy. I mean, it's disappointing because what I really wanted to do was just have this predictive model up and have the race and just have it like side by side and be like, boom, look at that. Boom. I
Right.
predicted that pit stop.
Right, you predicted that pit stop.
But,
yeah.
I mean,
And-
if it doesn't work, it doesn't work. I
Right,
tried.
or you predicted that the guy didn't do it and then he lost, or
Yeah.
whatever, or he, yeah, something like that, but.
Would have been nice.
But I think you still have a good portfolio of stuff that if you were showing an employer or a,
Oh, no, I feel,
something that I think, you learned lots of stuff. Even sort of, you ran so many different models, you learned a bunch of different kinds of models because none of them worked.
and that's the thing is like, I never had a Bayesian statistics class before. And the only Python class I had was Dr. Sean Shaw's,
Yeah.
Except for the one in like 2013. So doing all this work in Python and teaching myself this Bayesian statistics method, I mean, I think that's pretty cool.
I had a small question. I'm sorry.
Go ahead, Sterling.
The Bayesian statistics, that's what I was concerned about when you had demonstrated the equation that you had used in order to evaluate when would the pit stop. You mentioned something about the alpha that was in there.
Oh, the alpha.
Yeah, that was for the negative binomial, not for the Bayesian.
Yes, this one right here. Oh, okay. So this is for the negative binomial. Okay. Did you say you came up with this equation to use it, or how was it evaluated?
I'll take credit for it, but no. No, this was in a book on negative binomial regression written by Joseph Hilby. He was a professor, I think, at Arizona State and a member of some statistical societies.
Oh, okay. And this was okay.
And
And this was,
the big thing is it's weird that it's negative.
Yeah.
Yes.
That,
all right. That's what I was. Okay. Thank you.
Really not that far off negative though.
No, it was negative 0.02.
Right.
yeah, but
Yeah,
any negative is weird.
I'm just trying to think, cause I've done something similar to that, and it is possible to have the negative value, but cause depending on alpha value close to 0, alpha value close to 1, it has some kind of over dispersed and less dispersed, whatever. But sometimes it has a negative value, and I believe it is actually treated like close to 0,
Okay.
something like.
Right, I think, it was
I think-
0.
I
But
think that was.
okay.
I'm not sure. 15 years.
I just did some brief research because I was like, I think this should be above 0.
Yeah.
So I was like,
Yeah, I think I ran into kind of similar, especially like a simulation study, that there were a whole bunch of them are actually slightly negative value. Yeah.
all right.
any other questions? Dave, you've been quiet. I guess this is your first time coming to one of these. All right, any other questions online? All right, well, thanks. This is good. Thank you. Those of you in the room and on Zoom, remember our last set of theses for this cohort is coming up on Thursday, July